Welcome everyone to this video, and today is part one of the gradient of any 3D line or function. Today we're going to be covering partial derivatives, and this is basically by the end of these two videos. I hope that you are good with some of the easiest parts of vector calculus. Also, I hope you're comfortable with partial derivatives by the end of this video, and please do subscribe and like if this helps you at all. Okay, so what is a partial derivative? In Calc 1 and 2, we covered things in 2D. For example, the integral of x squared dx is equal to x cubed over 3. That's in 2D because, well, x squared is just two-dimensional. But a partial derivative is for any amount of dimensions, any amount of variables. For example, we could have f of x, y, z. That would be three-dimensional. Or we could have f of a, b, c, d, e, f, g, ... until z, and it wouldn't matter. The only problem is that this is only along one axis. So for example, we could find, if it were this 26 variables, we would only be doing it in respect to one. And a quick note, since the rate is just the rate of change along one axis, that means we're not finding the gradient, we're just finding the rate of change along one axis. There is a difference. Later I'll be explaining specifically how we can find the gradient of a function, but it's not just the partial derivative of in respect to anything. So let's talk about notations. You might remember these from standard derivatives. From standard Calc 1 and 2, f prime of x dx over dy. And now let's talk about the partial derivative ones. So this, you might think, oh, just df over dx, right? That's normal. But if you notice, it's actually a curved d. And you might be wondering, what is f doing here? Isn't it usually f of x? And yes, that's true. If it was c of x, y, z, then we would have c over here, and and this is actually not d. We say partial, so it's partial f over partial x. And if it were c, if we had c of x, y, z, then we would say partial c instead. And over partial x just means in which respect to. In which variable we put it in respect to. For example, here it's in respect to x. If it were in respect to y, we would put y. Next, here we have f sub x. Same thing. If it were, we could replace f with c if we were using this function, and also we could change x with y if it were in respect to y. Next, let's talk about high order derivatives. So if we wanted to find, the second derivative, we would put partial squared f over partial x squared. My bad, this is not a partial symbol. And here we would just do f sub x. And what about, since we are many variables, what about if we wanted to do first with respect to x and then with respect to y? How would that work? Well, we would do partial squared f as usual, but instead we would do partial x, partial y, and here we would do f sub xy. Next, I just want to talk to you about something quickly. Any higher order derivative, it does not matter. So if we have partial f over partial x, partial y. By the way, I just wanted to say, for this video, I'm going to be using the normal Leibniz notation, just for derivatives, since for me it's easier and I learned it that way. If we first find the partial derivative of dx with respect to x, and then with respect to y. That is the same as finding it first in respect to y. So if we find the partial derivative with respect to x, then with respect to y, that is the same as finding it with respect to y, and then in respect to x. Okay, so next, how do we use, or how do we calculate a partial derivative? So if we had partial f over partial x, and we had the function x squared y squared, you might be thinking, well, genuinely have no idea what to do. All of this is really asking us to do, since it's with respect to x, is it's asking us to think of y to any power, basically this whole function, this whole part of this function, as a constant. So usually I just say, if you see anything that's not whatever's it's in respect to, for example, in our case it's in respect to x, I just put any other variables are equal to 5. So y is equal to 5. So the partial derivative of x squared y squared would be 5x squared. What's the derivative of 5x squared? It is just 10x. So instead of writing 10x, you actually have to substitute y back in. In this case, it's y squared. And we get 2xy squared. Next, what about if we have x derivative y? Then we would just do, since it doesn't matter which way we do, I like to first differentiate in x, and we've already differentiated it, partial differentiated it in respect to x. I'll just do y next, which would be now 4xy, sorry. Okay, so next let's say f of x is equal to cosine of xy. So first let's solve partial f over partial x, or we just solve it in respect to x. If you remember, we just treat y as a constant, and since we just treat y as a constant, how about we say cosine of 5y, just replace y with any constant, since it's just easier for me to see cosine of 5x rather than cosine of cx, c being a constant. So let's solve this. Well, if you remember, and also now you just need to find the derivative, no partial derivatives at this point, if you're just finding cosine of 5x, derivative of cosine of 5x. If you remember the chain rule, it states that it is, if we have f of g of x, and we wanted to differentiate it, it is equal to, we could just say that this is u, the inner part, and multiply, and just find the derivative of cosine of 5x, and then we just multiply cosine of u. We just say that the inner part is u, and we just multiply the derivative of the inner part by this. So what is the derivative of cosine of u? It is equal to negative sine of u. Next, we just see what is the derivative of 5x. It is just 5. So now we have negative 5 sine of u. And we just replace that with u equaling 5x. So we just replace that with negative 5 sine 5x x. And if you remember, we plugged in y equaling 5. So all we need to do is we just need to replace any 5s with y. Thus we get negative y sine of xy. And that is our answer. You've just solved your second partial derivative. Okay, so we already know what the partial derivative with respect to x of cosine of xy is. So how about we find the partial derivative with respect to x then with respect to y of cosine of xy. So we already know what the partial derivative with respect to x of cosine of xy is, and we know that partial derivative of x then y with respect to x then y is equal to the partial derivative with respect to y then x. Is that equal? So we can just, since we already know what the partial derivative with respect to x is, let us just find what the partial derivative of this is with respect to y this time. So you might know that if you multiply two functions, you use the product rule, and if you have a composite function, you use the chain rule. So first, let us do the chain rule for this. Well, we would just do the derivative of sine u, and then we'd do the derivative of x, y. The derivative of sine u is equal to cosine of u, and then the derivative of xy is just equal to x. So now we have x cosine of u, but we replace it with xy, so we have x cosine of xy. Next, we use the product rule, which is the derivative of u multiplied by v, add the derivative of v multiplied by u. So let us just apply it. So we know that the derivative of negative y is negative 1, so it's negative 1 multiplied by sine xy, so negative sine xy. And then add, what's the derivative of sine xy? Well, we know it is x cosine of xy multiplied by negative 1, is negative x cosine of xy. Sorry. Next, we just know that this is negative sine of xy, and plus negative is just negative x cosine of xy. Now that is our answer. I was just reviewing it, and I realized that negative x multiplied by it's not negative x multiplied by cosine of xy, since it's we don't need to find the derivative of u. I did the derivative of u, the derivative of negative y, which is negative 1, but I realize now that's just u, the function itself. So the actual answer is negative xy, since instead of multiplying it by negative 1, we multiply it by negative y. So our final answer is negative sine of xy subtract xy cosine of xy. And that is our answer. Now, since this was an introductory part, and this was just to get you in the flow of how we can measure a 3D, how we can find the gradient of a 3D function, I think we should just include how we can use, since it would work with our partial derivatives. But next time we'll be going over more detail. So well, believe it or not, the gradient of f of any function f of x, comma y, comma z a 3D function would be the would be a vector, the partial derivative with respect to x, comma the partial derivative with respect to y, comma the partial derivative with respect to z. And you might be wondering, well, that doesn't make sense, but it intuitively it does. Well, imagine we know what the definition of a partial derivative is if it was with respect to x. So if it were with respect to x, we would be finding the rate of change only along one axis, only along the x-axis. And since we know what the rate of change along the x-axis is, the rate of change along the y-axis is, and the rate of change along the z-axis is, we now know the rate of change, not the rate of change, the general gradient at any point of the function. Also, we could actually write this as partial if it were a unit vector, which it is. So we could also write it using this form, but most people write it like this. Okay, you know what? I think we should just cover one simple example, and next video we'll move on to more difficult examples. So imagine we wanted to find the gradient of x comma y comma f of x comma y comma z is equal to x plus y plus z. Well, we know this. We know the definition, or that the gradient of f of x comma y comma z is equal to the vector partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. So first we find the partial derivative with respect to x. We treat y and z as constants, but you remember the derivative of any constant is equal to 0, and we would use the power rule and we'd find out that this is just equal to 1 if we do it with respect to x, 1. And it's the same with y and z. So we know that the gradient for any point is 1, 1, 1. Thank you everyone for watching. I hope you enjoyed, and please do subscribe and like if you learnt something.